Sir Isaac Newton, one of my science education heroes. Neil deGrasse Tyson and I both agree this guy should probably be considered the greatest scientist of all time. Let's talk about why that is. And by the way, for the record, if you are, I guess whether you're in my class or not, what I've done in this chapter, if you think, gosh, he's going awfully lightly over Newton's laws and Kepler's laws, I'm going to separate out basically and do a separate chapter on celestial mechanics. So all of the math, all the physics, we're going to do separately in class. I just think it's a better way to do it. So this chapter, I'm really focused just on the history, in case you're wondering. That's why we're going to kind of not get too in depth and on the law of gravitation and so forth. Anyway, let's talk about Newton. You think of Newton, what do you think of? Well, you may think of the apple and gravity. And as you see here, Newton was born actually on Christmas Day, 1642. And actually born the year Galileo died, interestingly enough. We think of gravity, of course, when we think of Newton, and there's the legendary story of him seeing an apple fall, which may have been true because he actually had been in college in London when the plague swept through, and he was forced to flee back to the countryside where he grew up. And while he was there, he made a connection that nobody else had made. And remember, going back to Aristotle, people tended to look at the events on earth, on the ground, as being totally separate from the events in the heavens. And Newton seeing this apple fall, you can imagine him looking up and at the same time perhaps seeing the moon out and suddenly making a connection that perhaps the same force that pulls that apple out of the tree is the force that's controlling the moon. Nobody had put that together. I mean, it may seem obvious to us now, but nobody had put the two realms together. Now, this occurred, as you can see, when Newton was a very, very young man, but he didn't work out the law of gravity. He didn't have that kind of skill at that point, the mathematical skill and so forth to do it, but that's when he started thinking about it as a young man. Now, for the next 20 years, Newton lived practically as a recluse. He'd kind of been embarrassed at one point early on in his college career, I believe, and he really became kind of a shut-in. And during those years, though, he managed on his own to make so many brilliant discoveries that were destined to change the world. And I can't think of many people who've had a greater influence on modern civilization than Isaac Newton. Well, interestingly enough, a man named Edmund Halley, yes, Mr. Halley's Comet himself, was studying comets, and he needed to understand gravity in order to understand comets. And he got together a little crew at the local pub and said, hey, let's put together the best minds of our age and see if we can figure this out. And somebody suggested going to visit Newton, who, again, was this kind of oddball, this kind of recluse. And so Halley went to his house and explains to Newton, hey, this is going to be such a great discovery. Let's all work together to see if we can figure it out. And Newton literally says, oh, yeah, I know how gravity works. So he hadn't shared it with anybody. And Halley didn't believe him at first. And then Newton eventually, showed him the paperwork. And he was stunned. He said, well, you need to share this with the world. And Newton still was resistant, didn't want to do it. And Halley actually paid with his own money to have Newton's great book published, the Principia, which stands short for like the natural philosophy of mathematical principles, something like that. Anyway, in 1685, landmark book. It's probably most well known as being the basis of what we call Newtonian mechanics, like the whole field of physics. If you're in high school, then that's your entire first semester at least of physics. Anything you do with mechanics really comes from this book in 1685. It's remarkable. It could very well be the most influential science book ever written. I think the only ones I can think of off the top of my head, that would compete with it, obviously, Starry Messenger by Galileo, on the origin of species, Charles Darwin, maybe Einstein's book on relativity, but it's in good company. Now, if you're not impressed, okay, obviously this is the basis for a whole lot of physics, but if you're not impressed with that, check this out. in order to learn the physics, Newton basically taught himself mathematics. After a few months, it's thought that Newton was the greatest mathematician on the planet. And then it got to the point, once he knew all the math there was to know, let that sink in for a minute. Once he knows all math that exists at the time, he invents new math. Now, how smart do you have to be to do that? And in case you're wondering, the new math that he invented is what we now call calculus. Later on, a guy named Leibniz, once again, Newton didn't bother to actually publish this, his new mathematics, and later on, once a guy named Leibniz sort of independently discovered calculus, this caused a bit of an uproar when Newton said, hey, buddy, I figured that out 10 years before you, which led to a dispute. But anyway, still not impressed. So again, keep in mind, Newton is an absolute unparalleled giant in the world of physics. He's a giant in the world of mathematics. And just in case you're wondering, yes, even in astronomy, Newton invented a new type of telescope, what we call today a reflecting telescope. He's the first person ever to use a mirror. So when I talked about Galileo, I talked about how you could envision telescopes at that time being like an old pirate movie where they have the handheld, thing like this, and they're looking in it. And there's just two pieces of glass on each end. That's a refractor. Newton thought to use a reflector, a curved mirror at the bottom of the telescope, and then have the light bounce out the side of the telescope. Well, it turns out that for making large telescopes, it's a lot easier and a lot better to use a mirror than to use lenses. So basically, every large telescope in the world today is a descendant of Newton's original little reflecting telescope, including like the Hubble telescope, for example. So the man was a giant in physics, a giant in mathematics, a giant in astronomy. I just don't think anybody will ever top that. I just don't think you can, in our specialized world today, it takes so much to become a specialist in any one area. It's hard to imagine somebody being so influential in so many different areas. Anyway, very briefly, again, I'm going to go over this in a whole different sort of chapter now. The three laws of motion that he came up with in his book. First of all, the first law, inertia, he didn't actually come up with, just for the record, for historical record. The first part says if an object's at rest, it's just going to sit there until something comes along and moves it, essentially, until there's a net force on it. And that's something even Aristotle got right. The second part of Newton's first law talks about when things are already in motion. And in that case, this one is kind of surprising. The object will continue in a straight line at constant speed. Now, to give credit where credit is due, that actually was discovered by Galileo, but we still call it Newton's first law. So in his summary of motion, he said, look, if objects have no overall force, no net force on them, an object at rest will stay at rest. An object that's already moving will keep moving in a straight line at constant speed. That's not exactly common sense. That's my son passing by. That's not exactly common sense because, of course, if you throw a baseball, that baseball curves to the ground. But that's because it doesn't go in a straight line. But that's because it has a net force on it, gravity. If you roll the baseball across the floor, it slows down. It doesn't go at a constant speed. Why? Well, because there's friction and air resistance and stuff like that. So it's actually very hard to demonstrate this one. The best place to demonstrate it would be out in deep space. And then you throw a baseball and immediately would become clear that it's going to go in a straight line at constant speed. So we call all of that collectively Newton's first law. Here's just a silly thing here with a motorcycle, and the man has his own inertia. So just because the motorcycle stops doesn't mean that he's going to stop, which is why we wear seat belts and why we have airbags and so forth. Anyway, very quickly here, Newton then, a law that he did come up with was his second law that said, okay, what if there is a net force on an object? And in that case, you end up with this very deceptively simple equation. The net force is equal to the mass of the object times its acceleration. Deceptively simple because finding the net force is often a tricky proposition, as high school physics students find out pretty quickly. But anyway, today we measure that force in newtons. That's the science unit for that, the metric unit. In everyday life, we use something different. We use often use pounds. Yeah, so when you're weighing yourself, a pound is the equivalent of a Newton, like a mile and a kilometer. So anyway, and then his famous third law, maybe the most famous of his three laws of motion, the famous action-reaction. Most people learn it as for every action, there's an equal and opposite reaction. Not exactly what Newton said. Newton actually said for every force, there's an equal and opposite force. So many great examples of this. Basically, you couldn't get anywhere without Newton's third law. When you walk, what are you doing? You're actually pressing back against the earth in order to move forward. Anything that moves. A jet, the air goes out the back and the jet goes forward. A boat, the propeller spins, pushes the water back, the boat goes forward. When you swim, you push the water back so that you can go forward. That's motion. That's how it works, all due to Newton's third law. Another great example, of course, every rocket ever made, whether it's a bottle rocket on the 4th of July or a SpaceX Falcon 9, it doesn't matter. Rockets work the same way. Fire goes out one way, rocket goes the opposite way. Another great example is the Earth and the Moon. If you ask somebody, is there more force on the Earth or on the Moon? And the correct answer is there's an equal amount of force on both. So a lot of my students will be like, well, how's that possible? Well, an equal amount of force doesn't mean the result is equal. Yes, there's an equal amount of force on both, but the Earth weighs about 81 times more than the Moon. So the Earth ends up throwing the Moon around it into orbit. The Moon, all it can do with that amount of force is basically pull the Earth's water out a little bit and cause our tides, along with the sun. So, yeah, the result is not the same. The result is not the same, but the amount of force on each is the same, which is pretty neat. All right, so there's the beautiful space shuttle launch there to illustrate the third law. Have a lot of fun with that one in class, demonstrating that. All right, very quickly on the law of gravity. A couple basic things. The real basic theory here of gravity, and this was really probably Newton's greatest accomplishment, is that all mass has gravity. All matter has gravity. That's a huge finding. When you look at this equation, there's nothing in the equation that says mass of planet, mass of star, mass of moon. No, it just says mass. Everything, including you, has gravity. This was first proven experimentally by a guy named Cavendish back in the 1700s. And I'll show you a little bit of that experiment in just a second. Gravity is an attractive force. That's all it does. It only attracts things together, period. We don't know why. I mean, if you think about it, magnetism doesn't work that way. Opposites attract, likes repel. Gravity only seems to attract. Kind of mysterious. And this one might surprise you. Gravity is the weakest force in nature. Yeah, it's way weaker. Think about it. Your refrigerator magnet is defeating gravity right now. A little bitty magnet like that is defeating the gravity of the entire Earth. That's how weak gravity is. And all of these things are still somewhat a mystery. How gravity fits in with the other fundamental forces of nature. Now, to give you some reference of how weak gravity is, there's something called the gravitational constant, or as everybody calls it, big G. Big G is actually a really, really, really tiny number, very close to zero, which kind of illustrates how weak gravity is. This is a modern version of Cavendish's experiment. Wow, I'm really having a hard time with all my little video clips here. But anyway, he just showed that you had a couple lead balls that would actually attract each other. They actually pulled each other together, showing again that everything, all mass, has gravity. That's just a little clip from Family Guy there. Also a little joke about gravity there with Peter. Anyway, let's take a look at the equation here in a second. The equation basically tells us, look, more mass, more gravity. That makes sense. You would expect, more massive planets to have more gravity than less massive planets. And it turns out if it's twice as massive, it's twice the gravity. The math is easy. The distance, just like you'd expect, if you get farther away from a planet, you're going to experience less gravity. But in this case, it'll obey something called the inverse square law. And we're going to go over that in class a whole lot. A lot of things in nature behave according to the inverse square law. We'll have a lot to do in class in terms of orbital velocity and all that, but I just wanted to talk about the history of Newton. So much great history there I didn't get to, but now we're going to concentrate on the physics in class. Thanks for listening.